Great. Can you see my slides? Perfect. So yeah, thanks so much, Anna, for the very kind introduction. And I'll make sure to highlight some of the winter findings from my research too, because maybe the comments that you made are actually more relevant than you would think in terms of the winter warming. So as Anna alluded to, I am a postdoctoral research scientist at Columbia University's Data Science Institute. I'm also affiliated with the Climate School, and I kind of bridge between data science, climate science, and behavioral medicine and behavioral health. I'll talk a little bit today about a few insights, that have emerged from my research that I think are relevant for circadian scientists and for sleep researchers broadly. And one of these insights is that the environments that we inhabit, our primary habitats, are also experiments that are unfolding in time and space. And if we were to, zoom out and don the perspective of, say, an astronaut on the ISS looking down on Earth, you would see this experiment unfolding in real time at a very, very large planetary scale. And this experiment is one that is probably worth studying. And, back in 1957, Roger Revelle, who was really an early pioneer in climate science, he helped to determine the limit of the upper limit of how much CO2 the oceans can absorb. And he said, human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past, nor be reproduced in the future. And given that this experiment is unfolding, again, we should think really critically about what are some of the variables of environmental change that may be relevant for our health, our well-being, and of course, sleep. And so we are going through this period of rapid urbanization. Over half of humanity resides in cities today. The UN projects about 66% by mid-century. And we also are living through a period of large-scale connectivity and digitalization. So about 6.5 billion people have smartphones today. And that's 85% nearly of the human population. I think if you updated those statistics to today, we would be up or north of that measure. Just an astounding proportion of the human population that now is also connected through digital devices. And we are living through a period of climatic change as well. And of course, this is central to the talk today, that we are living in a world that has already increased by 1.1 degrees Celsius since the 19th century, but we expect between 1 to 6 degrees Celsius of warming on average around the world by the end of the century, depending on the emissions decisions that are made in the imminent future. And so this is kind of the cone, the trajectory that humanity is on. You can think of the spaceship Earth that we all inhabit, which is our home, of course, that we know. This red cone that you can see in this recent Nature report here really outlines the more plausible paths that we can take. Of course, we're very concerned and should be very wary of the full cone that you can see there that goes up to 6 degrees Celsius of warming. But the most plausible warming is around 2.5 degrees Celsius, and this ranges upwards close to 4 degrees Celsius at the sort of higher end and closer to 1.5 degrees Celsius at the lower end. And what's really interesting is that this, trajectory will largely depend on whether people can actually live up to the word of their, planned reductions and their commitments to reduce these nationally determined contributions to reduce their emissions. And what we can see is that we're on a path right now outlined in black on the left of this plot, but actually to limit warming to the thresholds that have, really been the target of recent Paris Accord and the aspirations of society, we would have to sort of embark on greater reductions than what we've seen. And so this just puts into perspective the task ahead in terms of decarbonization is quite an immense one. And these environmental changes that I alluded to are all happening, at the same time. One of the interesting things, if you look, just in terms of a recent warming, I like to update this plot continuously, and you can see that in 2023, the black line at the top of this plot really extended outside of the recent historical record, which you can see below, color coded by the average warming over the course of the last 70 or so years. And now updating this plot even further, looking back at January, we just saw the warmest January on record, again in the historical record. And so what's happening now is that we're basically breaking new records almost every single month. And it's important to realize and put this in perspective that we would expect, even though these are exceptional months, that really in our lifetimes, these will be some of the coolest temperatures really that we experience with the already committed levels of warming, let alone some of the more extreme ones that are still possible but less plausible. Okay, so what can we learn from all of this? Well, one of the key insights, I think, for behavioral researchers is that the future actually is already here. We talk a lot about warming in the future, but this future is just not very evenly distributed. And one of the ways of thinking about this is that as the climate warms, we're starting to see some of these very extreme events emerge at the tails of local weather distributions. The 2021 Pacific Northwest heat wave was one such event that is really characteristic of the type of emerging extremes that we're seeing more and more around the world. This event took place in the summer of 2021. It, transcended multiple boundaries. So it took place in Canada and in the northern United States and broke all-time temperature records in many places by upwards of 5 degrees Celsius, just an extraordinary extent. And this event baked much of the Pacific Northwest and was found to have been made 150 times more likely by human-caused climate change. The World Weather Attribution Report found that this was virtually impossible without human-caused climate change. And the event really hit the all-time, high mercury level, or broke the all-time temperature record in Lytton. So the center of this heat dome was located right over Lytton, British Columbia, in Canada, no less, where the temperature reached almost 50 degrees Celsius, just an extraordinary magnitude in the site of the indigenous village of Comsheen. As I think some of you know, the very next day, 90% of Lytton was destroyed by a heat-induced wildfire. And this is, just a street view image in the neighborhood before, and then in the same position following that day and those tragic events. And I think one of the things that's really important is that the scarred and charred remnants that you see here really are atypical when it comes to a lot of the impacts of heat. Many of the heat-related impacts on human health are seldom so visible, certainly in the landscape, as what you would see here with the sort of debris trail following a fire, or say the debris trail following a tornado. Many of the pieces that are left behind by heat extremes and heat stressors, researchers and epidemiologists have to kind of follow and pick up those pieces for many months and even years after the event to really determine what happened. And this is even though heat-related natural disasters are the largest cause and largest source of loss of life in the United States. It remains to be the case that they're hard to track and cover the same way, certainly in terms of public attention, as some of these more salient and short-lived disasters like a hurricane or a tornado. And so what we can see is that that event led to about 868 heat-attributed deaths. The emergency department visits were 60 times higher in these affected U.S. regions compared to the same time of year without the extreme events. But this entire sort of cascade of events and impacts raises the question: what was the hidden behavioral burden? And in the recent Lancet Countdown report on health and climate change, we actually developed an indicator to look at some of these hidden impacts on mood and sentiment. And what we did is we linked the universe of geolocated social media posts on Twitter, so 8.2 billion social media posts from over 190 countries, almost every single county on the planet, in 13 different languages. And we use natural language processing and a sentiment dictionary to basically count the positive and negative expressions in language that were manifest in these social media posts. And we ran a global scale natural experiment where we compared what happened to local rates of positive and negative expressions when counties were randomly exposed to randomly timed heat wave events. So again, the timing of these heat waves events would be as good as random, and we'd compare those rates to the expressions in that same place at the same time of year. So really using the quasi-experimental sort of framework here to figure out what the impact actually was of these heat wave events. And what we could see is that heat waves worsen sentiment, so they amplify negative sentiment, and they also reduce positive sentiment and expressions. And just to put this in perspective, which I think is relevant for the community and circadian science broadly, heat waves, a single heat wave event in 2022 amplified the negative emotional expressions by over 5 times the effect of daylight savings time, which just puts it, I think into perspective. Unlike DST, these heat wave events can take place for multiple days, and they oftentimes will, recur throughout the course of the year. And so this is, a fairly large societal impact. Now, we might, raise the question, well, won't people in the more affluent and richer areas just buffer themselves from these types of effects? And what's interesting in the case of the Pacific Northwest heat wave event that I alluded to at the start is that it took place in one of the wealthiest parts of the world. And what we could see is that compared to the average heat wave event, that sentiment was worsened by an order of magnitude larger during that 2021 Pacific Northwest heat wave event, suggesting that some of these climate extremes that are emerging at local tails of weather distributions can actually exert very large impacts that are quite nonlinear compared to the historical trend. And so, again, these results suggest that these emerging extremes should be taken seriously and that they can induce large impacts even in some of the richest regions. So, as researchers, we might ask the question, why? What is actually driving this response that we can see people's language is becoming more negative? There's some other, evidence that other measures of self-reported well-being and self-reported emotional states also become worse in hot weather. So what might be the primary mechanisms linking these ambient temperatures with downstream adverse mental and behavioral outcomes? Now, if we think about this, high ambient temperatures have been found through epidemiological and economic research to adversely impact sentiment, as we just discussed, but also a number of other really important human outcomes. So different measures of mental health, both in terms of short-term hospitalizations, self-reported mental health, interpersonal conflict, both as measured through gun violence, physical violence and altercations, domestic abuse, interpersonal conflict in terms of gang violence, and even civil war. All of these have been found to be sensitive to hotter than normal conditions. And we also know that local rates of suicide increased with heat around the world. This is a very global phenomena that now has been established in multiple countries, that there's a quite linear relationship between temperature and rates of suicide. At the same time, we know that learning performance in schools and on high stakes and low stakes examinations declines in hotter weather. We know that labor productivity in both factory and other commercial settings declines during hot weather as well. And we know that occupational and all-cause injuries also go up in the population, and that mortality rates also spike on hot days. And so, why might this be? Now, one potential hypothesis here is that insufficient sleep is associated with these very same outcomes and may be one potential pathway, that we should investigate. Now, another motivation for thinking about sleep as being one potential plausible pathway here is that actually, if you look at the rate of warming around the world, what you can see is that since the 1980s, nighttime warming has been sort of outstripping the pace or outpacing daytime warming across most global regions. And this is something which is taking place truly at a global scale due to human-caused climate change. At the same time, the exposure to nighttime heat is also being amplified and exacerbated by an increasing proportion of humanity relocating to urban environments and creating these human infrastructures that actually absorb energy during the day. And that energy is released primarily during the nocturnal resting period at night. And this urban heat island effect, of course, has been well characterized around the world. So there's really a double burden here. It's that the world is warming faster at night. There's also more people getting exposed to nighttime heat through urban environments. And you can see this through space. If you just look in the near infrared, you can filter on that across an urban area and see those urban areas actually light up at night because they are sort of exuding this waste heat. Okay, so at the individual level, thermoregulation also plays a very functional role in both falling asleep and remaining asleep. Now, this, core body temperature rhythm keeps us at a relatively stable core body temperature, but it does oscillate over the course of the day. And as we approach the time of sleep, our core body temperature declines. And this is strongly correlated with sleep onset. And also, this core body temperature will remain low until it rises again right before awakening. And at the same time, before humans go to sleep, our distal regions will actually vasodilate and help to displace core body temperature or core body temperature into the surrounding environment. So we will shed waste heat into the surrounding environment, assuming that environment is cooler than we are. And so that thermal gradient from really the core to the surrounding environment plays a really functional role at night in terms of allowing the body to drop its core body temperature. And it's been shown in the sleep laboratory and in controlled experimental settings that the duration of wakefulness increases really outside of this thermoneutral zone. So this Goldilocks zone, if it's too cold or too hot, what you can see in the sleep lab is that people will sleep less. But one of the limitations here is that we don't really know what happens in the real world. That is, if we do not constrain adaptive behavior, how do people respond to fluctuations in temperature when they're going about their everyday lives in this sort of ecologically valid settings that are very unlike what you see here through, classic gold standard polysomnography. And so, thinking about the prior literature on this subject, there are two large-scale studies that have been done with self-reported measures of sleep. Both Abradovich et al. And also Mullins and White used nationally representative time use survey data, as well as the behavioral risk factors surveillance survey in the United States. And they found that, randomly timed periods of hotter temperatures reduce self-reported time slept, as well as increased self-reported nights of poor subjective sleep. And this is, again, just limited to the United States. And so we wanted to really expand on that prior literature by asking the question, do nighttime temperatures impact individual level sleep outcomes at a global scale? And to do this, this paper too I'll be talking about was recently published in the journal One Earth. If anyone needs access to that, I think there might be a paywall still. I'm happy to send an author's copy. And this paper coupled together 10.7 billion minute-by-minute sleep state observations from wrist-based accelerometry, sleep tracking wristbands between 2015 and 2017. These observations were aggregated into 7.4 million nightly sleep observations from 47,000 plus adults from 68 different countries around the world. On the left-hand side here, you can see the weather station data, and on the right-hand side, you can see the global distribution of the wristband data. And as you can see, there are entire regions that are not included here, and I think that's important to point out. much of sub-Saharan Africa is completely off the map, as well as large parts of Brazil. But still, in terms of global coverage, we have a diversity of different climatic regions included in this global sample. And if we just look at the within person sleep deviations across, a given year, what you can see is that, we see the sort of patterns that we would suspect, that people often will sleep more on the weekends and less during the work week. And we can also see that there's some seasonal smooth fluctuations here, as well as some spikes that might be responding to different societal and social events. And so what we want to do here is to develop, really a global environmental contextual model to study our theoretical relationship of interest, which is the effect of nighttime temperature on individual level sleep duration in a given region on a given day. And so, to conduct the ideal experiment here, we would randomly assign people to different climatic regions around the world and see how their sleep would respond. But one can imagine trying to convince a grant organization to buy tickets for people to travel around the world. Certainly, in the context of climate change, this would probably be viewed as blasphemy and a waste of public funds. And so, in lieu of that perfect natural experiment, we will think about how we might conduct a quasi-experiment to estimate this response. And the challenge here is that there are a lot of different unobserved time invariant individual differences, things like personality, differences in terms of access to air conditioning, other unobserved differences that might also spuriously sort of correlate with sleep duration and weather. And we also would want to, control for other geographic and time varying factors that we know as sleep researchers are really important for sleep. And so we use a multivariate fixed effects model where we leverage fluctuations in individuals' exposure through really space-time to variations in climatic factors. So you can think about this as leveraging within individual variation in both their exposure to weather and temperature, and within individual variation in their sleep responses. So we're really looking at the effect of an anomalous hot temperature spike, and then really regressing that or comparing that within individual spike in temperature exposure to their within individual change in sleep duration. So we're controlling for these unobserved individual differences. And one of the interesting things here is that we're also going to control for other time varying meteorological factors, things like precipitation, cloud cover, diurnal temperature range, wind. And we're also going to adjust for every single region by month time trend over the course of the study to account for other seasonal changes. And we're also going to control for every single date of the study. So that earlier plot that I showed you of the within individual variation over time, we're actually going to partial out those different changes due to things like day of the week, other seasonal variation, other societal events like weekends or holidays. We're going to control for those. And the remaining variation that is really left over here is as good as randomly distributed. And this is really important because that quasi-random variation is going to allow us to actually, interpret our coefficients here as plausibly causal effects of increases in nighttime temperature on sleep loss. And just to show, what this looks like visually, essentially, if we detrend or if we take out these controls from the temperature time series, what you can see is when we add these controls in green, what you can see is that the remaining variation in daily minimum temperature is as good as randomly distributed. And so what we find is that within individuals, exposure to a randomly timed, unseasonably hot night at temperature reduces time slept. And this increases across the temperature distribution. So in other words, once temperatures exceed 10 degrees of Celsius, we find that individuals lose about 0.61 minutes of sleep loss per degree, but this amount of sleep loss increases progressively and consistently as you move across the nighttime temperature distribution. And it's consistent in functional form, whether you measure this with weather station data or use gridded reanalysis data that basically fills in the gaps between weather stations. Okay, so where is the sleep loss actually taking place? When we actually break this down across the sort of sleep period and look at sleep timing, what we can see is that most of the sleep loss is taking place through a delay and when people fall asleep, and also in advance and when they wake up. We also see that mid-sleep is slightly pushed back, but that this is a very slight and marginal effect compared to the sort of movement on sleep onset and the advance in sleep offset. So what we can see is that the entire sleep period is actually being compressed as people are exposed to progressively hotter nighttime temperatures. I think also one of the very interesting things here is that we can look at clinical definitions of short sleep around the world. So whether we use less than 7 hours, less than 6 hours, or less than 5 hours, we can see that hot nights amplify the probability that individuals experience a short night of sleep. And just to provide a sense of scale, a single night exceeding 25 degrees Celsius here would expose individuals or expose an equivalent population of 100,000 adults. It would result in 4,600 of those adults having a short night of sleep. So an equivalent population of 100,000 adults on a single night above 25 degrees Celsius, we would expect that 4,600 adults would have a short night of sleep, just to put that in perspective. However, very importantly, we see that these effects are quite heterogeneous. So we find that the elderly were over twice as impacted per degree of warming compared to middle-aged and younger adults. We find that females are 25% more impacted compared to males, so significantly more impacted, but slightly in terms of that magnitude. And we also see that people who are living in lower middle income countries were approximately 3 times as impacted per degree of warming compared to people living in higher and upper middle income contexts. And this may suggest that there are different, unobserved adaptive amenities that are available to people living in those higher income contexts that help to buffer against this effect. But we do not see, even in the high income areas, any population here being completely immune to nighttime sleep loss due to warming temperatures. So this raises some really, thought-provoking questions, because the functional form that we've identified here, I think took us by surprise, the authors of this research. We had suspected that maybe sleep would be similar to mortality, that you would see this U-shaped response when it's really cold or really hot, people would, sleep worse. That's not what we found. What we see from that functional form is that the warmer it is outside, the less that people sleep, and that increases progressively across the global temperature distribution. So this raised some interesting questions about adaptation. Like, won't people just adapt in either the short or medium or long term? So when we looked at day level adaptation in terms of napping or daytime sleep, we found that actually, if you look over a 24-hour period, the sleep loss is even larger than just looking at the nocturnal period. And so then we looked at the week level to see whether people would just catch up on sleep loss. Say you sleep badly the one night, maybe you catch up on sleep in a compensatory way over the following days. But no, actually, we found that the cumulative effect was 30% larger at the end of 7 days, again, suggesting that those cumulative aggregate impacts were even larger than just the contemporaneous single night effects. So then we thought, well, maybe it takes multiple months for people to acclimatize, just takes more time for people to get used to these hotter temperatures. And what we did is we compared sleep to a randomly timed temperature shock at the beginning of summer to the end of summer, when heat is more cognitively familiar and less surprising. And what we found was that actually the impact at the end of summer was similar in magnitude and slightly larger than at the beginning of summer. So again, little evidence in the way of adaptation, but maybe it just takes a really long time. Like, plausibly, people who are living in the hottest regions in the world should be the best adapted to them. And those might help to reveal just how well humans can adapt. And we were really surprised when we broke out our results by deciles across the global climate distribution that people who were actually living in the hottest global regions were over twice as impacted per degree of warming compared to those people who were living in the coldest regions. And again, these are within individual effects, just stratified across the deciles of the climate distribution. Okay, so as I mentioned before, we can see that hotter temperatures amplify the probability of having a short night of sleep. We can also see that other meteorological factors are important for sleep, but the effects are not as large. So we can see as the diurnal temperature range, so the difference between minimum and maximum temperature on a given day increases, that people lose additional sleep. And this may suggest that when you have a really hot maximum temperature, that even if the nighttime temperature drops outside, that some of that residual heat is stored within the built environment, inside the rooms and houses and places that people spend their time and ultimately rest and sleep, that there may be some lagged storage that persists. And that may also contribute to what we saw before, that there's a delayed effect from a nighttime temperature shock that seems to increase and continue for several days over the course of a week after that shock. So how might future warming impact human sleep outcomes at the global scale under different greenhouse gas concentrations, given that we haven't found compelling evidence for, fast adaptation to hotter temperatures? So what we did here is quite simple. We just coupled our damage functions, the temperature sleep estimates from our primary regression, and we coupled those together with downscaled global climate model data from NASA around the world. And we did this for both a high greenhouse gas concentration scenario, RCP 8.5, and a middle of the road greenhouse gas concentration scenario where humans actually successfully stabilize emissions by the end of the century. And so that's RCP 4.5 in purple. And what you can see is that already at the beginning of the century, that people are losing about 45 hours of sleep per person per year due to suboptimal nighttime temperatures. But the amount of sleep loss due to suboptimal temperatures is projected to increase under both scenarios. However, the scale of the increase really depends on the emissions decisions that society takes. So we can see these higher greenhouse gas concentration scenarios, assuming that there's no additional adaptation in the future, would result in much, much larger sleep impacts compared to the stabilized emission scenario. And you can also see this if we look at the projected cumulative excess short sleep. So these are the nights of short sleep due to suboptimal nighttime temperatures. And what you can see again is that higher emissions scenario really results in a much longer tail distribution. So that yellow distribution starts moving progressively to the right. And that is an aspect of sleep risk that, certainly, we should consider as we think about what the, trade-offs are in terms of the costs and benefits of our, carbon decisions moving forward. Okay, so we can also do these projections at a spatial level around the world. And so if we just take the ensemble average of all of the grid cell level projections, we can see that as greenhouse gas concentrations increase, the disparity between the sleep loss due to nighttime temperature in the coldest regions and the warmest regions becomes progressively larger as a function of those scaling greenhouse gas concentrations, suggesting that some of the disparities in nighttime sleep loss due to temperature will increase in a warming world, again, without further mitigation or adaptation. So just to wrap this up, we found that rising nighttime temperatures in this global scale natural experiment both reduced and delayed sleep. And this was also true that the burden of heat attributed sleep loss appears quite unevenly distributed, both within the current population, but also projecting into the future, that future generations would appear to, bear the brunt of these impacts more than the current generation. And we also found that sleep may be one of these key mechanisms linking ambient temperature with some of the adverse downstream mental, cognitive, behavioral, and cardiovascular outcomes shown to increase on hot days. Again, we know through both sleep restriction and sleep epidemiological studies that these are really important pathways just for human welfare and well-being. And on the flip side, one of the takeaways of this study is that colder temperatures do seem to promote sleep gain, and this may be a low-cost target for adaptation if it's equitably addressed. Again, right now we don't see access to air conditioning, for instance, and cooling technologies existing in an equitable way at the global scale. And it's very likely that the estimates that I presented today are conservative. The sample that I reported on was composed of more people from affluent and richer countries. It was more male and more middle-aged population. All of those same subgroups that were less represented, even within the study, were much more impacted, as I showed in those subgroup results. So this is just an important caveat to mention. And I think, Anna, we're running, I think, a little bit over on time, or am I good? Okay. Um, if I have time, I think I'll just fly through some of these results from this new systematic review. If anyone's interested in learning more about this topic, I recommend you checking this out. This has been posted on medRxiv, and I think the final version hopefully will be out in a few months here. And what we did is we just were curious when we looked at the existing literature, what studies had been done around the world looking at temperature and sleep. So all sort of valid measures of sleep, that includes sleep quality and sleep fragmentation and efficiency, but also we were interested in both objectively measured measures of sleep from polysomnography as well as other device measures of sleep. And we identified 36 studies from our comprehensive review. I should say that we required that these studies be conducted in ecological settings. So again, we were interested in how people respond to temperature in their everyday environments and everyday routines. And what we could see is that the distribution of these studies was not very even around the world. There's much more coverage in the US, China, and Australia. And then we can also see that, huge parts of global population centers, especially in Africa, parts of the Middle East and parts of South America were entirely left off the map. And of the studies found, of these 36 studies identified in this systematic review, 81% of the studies identified negative sleep associations between high ambient temperatures and human sleep outcomes. And this was interesting that these impacts seem to persist across multiple measures of sleep. So not just sleep quantity or total time slept, but also measures of sleep quality, sleep efficiency, and self-reported and subjective sleep as well. So again, there seems to be an array of impacts from heat in particular. And we also found that, the existing literature, while, quite nascent and sort of emerging, still primarily measures temperature either outdoors or indoors as opposed to both. And I think there's room for a lot more research that systematically measures both of those variables, because it's very possible that the pathways leading from outdoor ambient temperatures and indoor ambient temperatures are entirely different. And so oftentimes ambient temperature gets thrown into the same sentence, but we really should be thinking about indoor and outdoor temperatures in different ways. And finally, even though 40% of the human population lives in the tropics, we found that actually a dearth or just a minority of the existing research actually has been conducted in the tropical regions. And this is another, opportunity, I think, especially for researchers to contribute. And even though there were 36 studies, the quality of these studies varied immensely. And there's a need for more research that employs repeated measures and quasi-experimental designs to estimate these, individual level responses across the life course, and also at different scales from the local to the regional, all the way to the global scale. And there's a need to think about which populations and subpopulations may be the most vulnerable and at the highest risk of experiencing some of these adverse sleep outcomes during these increasingly frequent and intense ambient heat events, such as those I described earlier. And we also need to investigate the sensitivity of these responses for people who have prior sleep and wake disorders. This is a really important opportunity, and I would throw in circadian science into there as well, that we need to better understand the implications of these stressors on the entire circadian system. And finally, there's a huge opportunity to test adaptive interventions and to help inform sleep adaptation to warming nighttime temperatures. And this is really a way that we can learn more about some of these mechanisms, but also develop insights to help populations adapt to this emerging nighttime stressor. So I think now, for sure, overtime. But I just want to say thanks everyone for staying on. And I thought I would just conclude with this really simple visualization, but I thought this is quite elegant from the 2023 IPCC summary for policymakers. So this is basically, scientists spend eons working on these climate reports, and then at the end of the day, people will just take like one or two slides away and try to like show policymakers and the public why we should be paying attention at all. And I think this is just helpful because the decisions that we make today really do have these long-term delayed consequences in terms of the future emissions impacts. And so, as we exist, at this juncture in time, we should really think carefully, not just what nighttime or climate change and global warming means for the population at large, but also what it might mean for our sleep in particular, and the sleep of people around the world at all different stages of life, and for people from vastly different means in terms of adapting to those nighttime temperature stressors. So with that, I will open things up for questions, and thanks so much again for staying on and having me on.